Okay guys, so in this video we are gonna talk about the reactions of chlorobenzene. Okay guys, so these reactions are also very important. Basically, they are just a few reactions of chlorobenzene that are repeatedly asked in the past papers. These reactions are very important. Chlorobenzene is basically a derivative of benzene with a chloro group as a substituent. So this is the structure of chlorobenzene, a chlorine atom with a benzene group attached. Okay, now first reaction is its nitration. When chlorobenzene is nitrated, again, the nitrating agent used is concentrated nitric acid, and the sulfuric acid, the concentrated sulfuric acid, is used as a catalyst. Temperature of approximately less than 55 degrees Celsius. We'll get two products. Okay, now let's before we proceed, keep in mind that halogens are, as we talked in the previous video of directors, that halogens are 2, 4, 6 directors, and halogens are an exception. The exception was that we know that all 2, 4, 6 directors are activating groups, but halogens are an exception and they are deactivating groups. Deactivating. So this is an exception of halogens that we need to keep in mind. Please learn this. Okay, it has been asked several times. What are halogens? Activating or deactivating? They are basically deactivating groups. Okay, guys. So now we've nitrated it with concentrated nitric acid as the nitrating agent. What happens is that the nitro group gets attached and is directed towards the second position or the fourth position or the sixth position. Basically, it gets directed towards the second position, and when it's get directed to the second position, it means that it's automatically directed to the sixth position because it's a 2 or 6, it's the same thing with respect to the first chlorine atom, because if we look at this carbon atom over here, it's second carbon with respect to this carbon, and sixth carbon is over here. So only one place is going to get nitrated, either the 2 or the 6th. Okay, now the second product that we have over here is 4-nitrobenzene, 4-nitrochlorobenzene. It's basically the nitro group gets attached to the fourth carbon atom over here. Carbon 1 is the carbon containing the chlorine atom, and then with respect to that carbon, 2, 3, and the fourth carbon is this one. So the name becomes 4-nitrochlorobenzene and 2-nitrochlorobenzene. So basically, these are the two products that we have, and again, they are in a 1-to-1 ratio. Okay, guys, so these two products are in a 1-to-1 ratio. Now, the next reaction that we are going to look at is a very important reaction. It's basically a reaction of chlorobenzene. I'm making chlorobenzene in horizontal direction. Chlorobenzene with NaOH, aqueous NaOH. Okay, when we react chlorobenzene with sodium hydroxide, no reaction is observed. No reaction is observed. And if we recall AS, the nucleophilic substitution reaction of alkyl halides, for example, if I have ethyl chloride and it is reacted with NaOH, the NaOH provides the nucleophile, the OH negative is the nucleophile from NaOH. It attacks the carbon atom with the partial positive charge, partial positive and partial negative difference in electronegativity. It attacks the carbon atom, and then this bond breaks, and as a result, through the SN2 mechanism, because of the primary alkyl halide, we had our final product as CH3 CH2 OH ethanol plus NaCl. This is a reaction from your AS level chemistry. Okay, so this was basically the nucleophilic substitution reaction. SN2 mechanism applies over here because it's a primary alkyl halide. Now, how did this nucleophilic substitution reaction occur in the alkyl halide but is not possible in the chlorobenzene? Now, why is this reaction not possible? Now, this is important. The why is important. Why doesn't this reaction occur? Now, let's see why. To see why this reaction is not possible, we are gonna need to look at the structure of chlorobenzene in a bit more detail. Chlorobenzene. Okay, we know that benzene has a delocalized pi system above and below this hexagonal ring. The chlorine atom has lone pair of electrons. Okay, now these lone pairs of electrons, they get delocalized over the benzene ring, forming an extended delocalized pi orbital because the chlorine atom has lone pairs, and since there is a delocalized pi electron system in the benzene ring, and the lone pairs are also there, and the lone pairs are directly attached to the benzene ring, so an extended delocalized pi orbital is formed. So the first point in our answer is there is an extended delocalized pi orbital that exists in chlorobenzene. Okay, now this extended delocalized pi orbital would mean that there is a dense electron density above and below the benzene ring, right? Electron cloud is basically electron density or electron cloud is present above and below the ring. Now we know that electron cloud is present above and below this ring. This basically the green outline is of that electron cloud that basically uh, overlaps actually the molecule or the structure which is in between them. Okay, what happens is that this carbon over here, which is directly attached to the chlorine atom, it is partially positively charged because the chlorine atom is partially negatively charged. Now, if there is gonna be a nucleophilic attack of OH negative on this compound, it is gonna attack this partial positively charged carbon atom because nucleophiles are attracted to regions of positive charge. Now, when the nucleophile will try to approach this carbon atom, the nucleophile has now, when this nucleophile will try approaching this carbon atom, since the nucleophile has a negative charge and this electron density is also negatively charged, the electron density will repel this OH negative and prevent it from approaching this carbon atom. So basically, repulsion in between the electron density repulsion between the electron density and the nucleophile prevents the nucleophile from approaching the partial positively charged carbon atom. And one more reason is that an additional point that can be added is that the carbon chlorine bond over here, the carbon chlorine bond, it gets a partial double bond character, a partial double bond character. Why does it get a partial double bond character? It gets a partial double bond character because the electron density over here, we know that electrons form the covalent bond. The electron density is spread over the entire ring and it's continuously spreading over the carbon chlorine bond as well, but is not stationary over there. So since the electron density is also spreading over the carbon chlorine bond, so it gives and is not present here permanently, it gives the carbon chlorine bond a partial double bond character. Partial double bond character would mean that the bond becomes stronger and more energy will be needed to break this bond, hence this reaction will become more difficult. So this increases the activation energy. So these are basically the 4 points that explain why this hydrolysis reaction, this nucleophilic substitution reaction of OH negative with chlorobenzene is not possible.